Welcome to our deep dive all about Java microservices with Quarkus and Kubernetes. It seems like you're really interested in learning how to break down those big monolithic Java applications into smaller, more agile microservices.
And that's definitely a smart move with all the buzz around microservices these days.
Yeah. And we've got some great material to help us out here. The book, Pro Java Microservices with Quarkus and Kubernetes.
Yeah, and it's great because it's not just theoretical. The book uses this practical example, the Quarkus Shop application, to show how it all works.
Oh, cool. Like a real world e-commerce app.
Exactly, a real world example.
Okay, awesome. So I was really drawn to the part about the challenges of updating like a product in the monolithic version of Quarkus Shop. It sounds like even a small change can cause a lot of problems.
Oh yeah, absolutely. It could become a huge headache. Imagine, you just want to update a product description, something simple.
Right.
But in a monolith, everything's so tightly coupled together
Oh, yeah.
that even a tiny change might mean you have to retest the entire application. And then you've got to redeploy the whole thing.
Right.
Which means downtime.
Yeah.
It can make the system unstable and you end up wasting a ton of time and effort.
Yeah, no kidding. That just kills productivity.
Yeah, for sure.
Like having to repave the entire highway because of one pothole.
Exactly.
I can see why people are moving away from monoliths.
Absolutely. Monoliths, they can become a real bottleneck as your application grows and your team gets bigger. They just don't have the agility or scalability that companies need these days.
Right. So microservices are the solution to all this monolith mess. I get the idea of breaking things down into smaller services, but how do you actually decide where to make those cuts?
That's where domain-driven design comes in, or DDD for short.
Yeah.
Instead of just hacking up the monolith randomly, DDD gives you a strategy for figuring out those natural boundaries within your application.
Oh, that's a good point.
Yeah. It's like having a blueprint from an architect instead of just swinging a sledgehammer.
I like that. So with DDD, we're talking about more than just technical divisions. We're thinking about actual business domains, right?
Exactly. DDD encourages you to look at the application from the perspective of the business. Different areas of expertise within the business, each with its own logic and data and rules. And we call these areas bounded contexts.
Okay, so can you give me an example of a bounded context in this Quarkus Shop application, something I can visualize?
Sure. Think about products, orders, and customers.
Okay.
These are all great examples of bounded contexts within an e-commerce application. Each one represents a specific area of concern with its own data and logic.
I see, yeah. So instead of one giant Quarkus Shop blob, we'd have like separate services for products, orders, and customers, each with their own clear purpose.
You got it. And by separating them out, we can develop and deploy and scale each service independently.
Yeah.
That gives us way more flexibility and agility.
It sounds great, but I can't help but think about all the different moving parts. Once you break down that monolith and you have all these separate services, how do you make sure they can still communicate and work together smoothly? It's like herding cats.
Oh, yeah, that's a valid concern. And that's precisely where containerization and orchestration tools come in. Tools like Docker and Kubernetes, they help us manage those cats and create a really well-coordinated system.
Okay, I've heard of Docker, but I'm still not quite clear on what it is. Can you explain what a container is and why it's so important for microservices?
Sure. Think of a container like a lightweight box, a portable box that holds your microservice and everything it needs to run. It's like a little mini environment where your service can run without any problems, whether it's on your laptop, a testing server, or in the cloud.
So each microservice gets its own little self-contained world to live in without interfering with its neighbors.
Exactly. Docker gets rid of that whole "it works on my machine" problem by ensuring consistency across all the different environments. And that's really important when you have lots of services talking to each other.
That makes a lot of sense. What about this thing called a Docker file? What does that do?
Good question. A Docker file is basically a set of instructions that tells Docker how to build your container image.
Okay.
It's kind of like a recipe that tells Docker how to take your code, your libraries, and your configurations and bundle them up into a portable unit.
So it's the blueprint for building the microservices little home.
Precisely. And the best part is Docker has this massive library of pre-built images for common software, like databases and tools, that makes it super easy to get started. The book actually shows how to use Docker to set up a PostgreSQL database in SonarQube for code analysis really quickly.
Okay, so I'm starting to see how Docker makes it easier to deploy and manage each microservice on its own. But what about managing all those services together? How do you make sure they scale properly and the whole system runs without any hiccups?
That's where Kubernetes comes in.
You got it. Kubernetes is our orchestration platform. Think of it like the conductor of an orchestra, making sure all the instruments are playing together nicely.
I like that analogy.
Yeah.
So Kubernetes helps you manage and scale all these Docker containers, right? But can you break it down a little further? What are the key concepts I need to understand?
Sure. So in Kubernetes, the smallest unit of deployment is a pod.
Okay.
And a pod usually holds one or more containers. It's basically a logical grouping of containers that work together.
So if a container is like a house, then a pod is like a neighborhood of houses that share resources and have a common purpose.
Exactly. And then you have deployments.
Okay.
These guys are in charge of managing the lifecycle of our pods. They make sure we have enough replicas of each pod running and handle updates and rollbacks smoothly. So if a pod is a neighborhood, a deployment is like the city planner, making sure there are enough houses and neighborhoods and handling renovations and stuff.
That's a great way to think about it. Then there are services.
Okay.
And services are how we access a group of pods, even if those pods get created or destroyed as we scale up or down.
I see. So it's like having a stable address for the neighborhood, even if the individual houses within it change.
Exactly. And to keep things organized, Kubernetes uses namespaces. Namespaces group resources together logically. It's like having different departments within a company, each with their own resources and access control.
That sounds like a good way to avoid conflicts between different parts of the system.
Yeah, definitely helps. Now, what about sensitive information like passwords? You wouldn't want to hard code those into your microservices code. That would be a huge security risk.
Oh, absolutely not.
That's where config maps and secrets come in handy. Config maps are for non-sensitive data, like configuration settings, while secrets are designed to hold sensitive information like passwords and API keys.
So config maps for things like database connection details and secrets for the really important stuff.
Precisely. And the best part is you can use these config maps and secrets in your deployments, so your sensitive info is stored securely and separately from your code.
That's really clever. Wow, we've covered a lot of ground already. From those monolithic nightmares to Docker containers and the incredible world of Kubernetes, it feels like we're building a seriously powerful microservices toolbox. What's next on the agenda?
Well, now that we have an idea of how to containerize and orchestrate our microservices, we need to make sure they're resilient and can handle the challenges of a distributed environment.
Right.
That's where cloud design patterns come into play.
Oh, interesting. Cloud design patterns. I'm curious to learn more about that. What are some of the patterns that help you create a really robust and resilient microservices architecture?
Well, let's start with the circuit breaker pattern. This one's designed to prevent cascading failures, which can be a real headache in a microservices environment.
Cascading failures. That sounds scary.
Yeah, imagine.
Yeah, cascading failures sound terrifying. It's like one service crashes and takes the whole system down with it. So how does the circuit breaker pattern work? Can you give me a concrete example, maybe from the Quarkus shop application?
Sure. Let's say our payment service, the one that handles credit card transactions, it starts having problems and becomes unresponsive.
Right.
Without a circuit breaker, other services that rely on payment, like the order service, would keep sending requests to it.
Okay, yeah.
And that would cause a backlog of transactions, timeouts, you name it. It would drain resources, and eventually it could even crash other services that have nothing to do with payments.
Yikes, that sounds like a recipe for disaster.
It is.
So the circuit breaker acts like a safety net to stop that domino effect from happening.
Exactly. When the payment service fails a certain number of times, the circuit breaker trips.
Okay.
Any new requests to that service get rejected immediately. That gives the payment service a chance to recover without being bombarded with requests and prevents the problem from spreading to other services.
Ah, that's a pretty clever solution. It's like a temporary firewall to isolate the problem and protect the rest of the system. So, what other patterns should we be thinking about when building microservices?
Well, another important one is log aggregation.
Okay.
When you have all these services spread across different containers, trying to troubleshoot problems by looking at individual log files would be a nightmare.
Ugh. Yeah, I can only imagine. That sounds about as fun as searching for a needle in a haystack.
Exactly. So log aggregation basically means collecting logs from all your microservices and sending them to a central location.
Gotcha.
That way you can easily search, analyze, and correlate logs from different services and get a clear picture of what's happening across the entire system.
So instead of a bunch of separate log files, we have one central source of truth.
Right.
That makes debugging and monitoring so much easier.
It does. And the book recommends using the ELK Stack, which stands for Elasticsearch, Logstash, and Kibana, to handle this. Elasticsearch is a really powerful search and analytics engine. Then you have Logstash, which collects, parses, and transforms log data from different sources.
Right.
And finally, Kibana provides a really user-friendly interface for visualizing and interacting with those logs.
So we've got our circuit breakers to prevent cascading failures, and we're aggregating logs to get a centralized view of our system. What else can we do to make our Quarkus Shop application even more robust?
How about tracking requests as they travel through our network of services? That's where distributed tracing comes in.
Distributed tracing. Okay, I'm listening. Tell me more about that.
Well, in a microservices architecture, requests often have to go through multiple services to get their job done.
Right, yeah.
Distributed tracing helps us understand this journey by attaching trace data to each request, capturing timing information and other relevant details. So as the request moves from one service to the next, we can see exactly what's happening.
So it's like giving each request a little passport that gets stamped at every service it visits.
That's a great analogy. And this passport allows us to visualize the path of the request. We can pinpoint bottlenecks and quickly identify the source of any errors.
Wow, it's like having a real-time map of our entire microservices system.
You got it.
Yep.
And the book recommends Jaeger for this, which is an open-source distributed tracing system.
Very cool. So we can prevent failures with circuit breakers, analyze logs with ELK, and now we can trace requests with Jaeger. What other tricks do we have up our sleeve?
There are a few more important cloud design patterns that we should talk about. For example, the API gateway pattern.
API gateway. That sounds familiar. It makes me think of some kind of main entrance to our microservices city.
That's a good way to visualize it. The API gateway is basically this single entry point for all external requests coming into your system.
Okay.
Think of it as the front door to your application, handling things like routing requests to the right service, enforcing security policies, and providing a consistent interface for clients.
So the API gateway is like the receptionist who greets visitors, directs them to the right department, checks their ID, and makes sure they follow the rules.
Exactly. Then we have externalized configuration, which is something we touched on earlier with those Kubernetes config maps and secrets.
Right, the idea of keeping all the configuration settings outside of the code. Why is that so important for microservices?
Well, think about it. In a distributed system, you might have many instances of the same service running,
Yeah.
and each one might need different configuration settings depending on the environment or its specific role. Externalized configuration lets you manage these settings dynamically without having to redeploy the entire service every time something changes.
So it's like having a central control panel where we can tweak the settings for different services and environments on the fly.
Exactly. Another essential pattern is the database per service pattern, which suggests each microservice should have its own dedicated database.
So no more sharing one giant database between all the services. Why is that a good idea?
For a couple reasons. First, it isolates the data, meaning each service has complete control over its own data and doesn't have to worry about other services interfering with it.
Okay, that makes sense.
Second, it gives you the flexibility to choose the right database technology for each service's specific needs. Some services might be best suited for a relational database, like PostgreSQL, while others might work better with a NoSQL database like MongoDB.
It's like each service gets to pick the database that best fits its personality. Are there any other patterns we should know about?
Oh, absolutely. We can't forget about health monitoring. In a distributed system, it's super important to keep track of how healthy your services are.
Yeah.
That means having health check endpoints for each service that can tell you whether it's running, responding to requests, and basically doing what it's supposed to.
So it's like having a doctor for each service, ready to give us a quick checkup whenever we need it.
Exactly. These health checks can then feed into monitoring tools that can alert you to any potential issues, allowing you to take action before they cause any real problems.
This is all incredibly helpful. We've gone from the mess of monolithic architectures to a well-organized, resilient, and scalable microservices setup. I feel like I've learned so much about building these systems.
I'm glad you found it useful. Remember, the book goes into a lot more detail about building the Quarkus Shop microservices with Quarkus, a Java framework made specifically for cloud-native development.
Yeah, we haven't even talked about Quarkus yet, and its supersonic subatomic capabilities. That's what I'm really excited to learn about.
Well, that's where things get really interesting. Quarkus brings a lot of performance benefits to the table, especially when we combine it with GraalVM for native compilation. We should definitely delve into that next.
Okay, supersonic subatomic Quarkus. That sounds pretty impressive.
It is. Quarkus was created to tackle some of those issues people have with Java in the microservices world.
Oh, okay. Like what?
Things like slow startup times and using up a lot of memory. Quarkus gets around these by using ahead-of-time compilation and cutting down on how much it relies on reflection.
Okay. I get that speed and efficiency are super important when we're talking about cloud native development, but can you explain what ahead of time compilation is, in simple terms?
Sure. So think of how Java usually works.
Mhm.
You compile your code into bytecode, and then the JVM interprets that bytecode at runtime.
Right.
Ahead-of-time compilation basically does a lot of that work during the build process.
So we're basically pre-compiling the code so the JVM has less to do when the application starts up.
Exactly. And that means much faster startup times, which is really important when you're working with microservices in a container environment.
I see. And this all ties into Quarkus's native compilation with GraalVM, right?
Yes. GraalVM is a high-performance virtual machine that can compile Java code ahead of time into a native executable.
Wait, so we can run Java without a JVM?
Yep, that's the amazing part. It means we can create these super efficient, self-contained executables that are much smaller and start up crazy fast.
No more waiting for the JVM to boot up.
Exactly.
That's pretty awesome. So with Quarkus and GraalVM, it seems like you get the best of both worlds, the ease of using Java with the speed of a native application. But are there any real-world tests that show how well this actually works?
There are. The book compares a Quarkus application running normally with one compiled to native code using GraalVM and a traditional cloud-native stack.
Oh, cool.
And the results are pretty impressive. Quarkus in native mode just crushes the others when it comes to startup time and memory use.
That's amazing. It sounds like Quarkus is changing the game for Java developers building microservices.
It really is.
Speaking of building, you mentioned earlier that the book's author ran into a problem with configuration files. What happened there?
Oh, right. It's an interesting point that shows how Quarkus is different from Spring Boot. The author was used to using multiple application.properties files in Spring Boot for different environments like development, testing, and production.
Right.
But Quarkus recommends using a single application.properties file.
So how do you handle environment-specific configurations in Quarkus if you can't use multiple files?
Quarkus has these things called profiles. You can define different profiles like dev, test, and prod right inside your application.properties file.
Okay.
Each profile can have its own set of properties, and you just activate the one you need when running your application.
That makes sense. Keeps everything in one place.
Exactly. And Quarkus also gives you ways to override these properties with environment variables, which is super useful when you're working with containers.
Well, this deep dive has been incredibly insightful. We've come a long way from those clunky monoliths to a well-designed and robust microservices architecture. I feel like I have a much better understanding of Java development now.
And I feel like we covered a lot of really valuable information about microservices. Remember, to build great microservices, you need to combine strategic thinking, technical skills, and a willingness to learn and adapt to new tools and technologies.
Definitely. To our listener, thanks for sticking with us on this journey. I hope this has given you the knowledge and the inspiration to start building your own amazing microservices.
Absolutely. Happy coding, everyone.